So in the last class, we have formulated the connection formula that connect the WKB wave functions at the classically allowed region and classically forbidden region. So the general solution that we obtain for classically allowed region is a solution of this form, which is in exponentially decaying e raised to minus I something. That means it's a sinusoidal function. So in the last class, we just reformulated it into sines and cosine like this. So this is a wave function that represent or WKB wave function that represent the classically allowed region. So here, exponentially decaying without that I factor over here, that represent the classically forbidden wave function of the classically forbidden region. So, and what we have seen is that okay, when you want to calculate the connection between the classically allowed region and classically forbidden region, uh, we have done the formulation, and finally we end up by having an expression, a function called airy function. And that function is having a peculiar property that at the asymptotic limit it can connect with the sinusoidal solution at one particular uh, situation. Another case, it can connect with an exponential solution. So depending upon the boundaries, asymptotic limit of the function, we have sines and exponentially decaying term. So these formula for our connection for the connection formula that we obtained here is actually an limiting cases that we applied for or asymptotic limiting cases that we applied for our airy functions. So we just put our quantities and reformulated in the way we want. And when we compare this equation, this is our connection formula that connect between uh, classically allowed region and the classically forbidden region, right? So one thing we can see is that the sine function, sine component, whenever you have a sine component in the classical region, that connect with a decreasing exponential. It is not connecting with an increasing exponential, it connect with a decreasing exponential. Whereas the cos term is always connect with the increasing exponential. Another uh, feature is that the amplitude, when you're connecting with the cos function, the amplitude is not really having any change. Exactly the same change, same value will come. But in the case where you're connecting it with the sinusoidal function, your amplitude, the exponentially decaying term, will be having half of the amplitude of that of the sine function. So that is a observations here. So this is a way we connect. Okay, now our aim is to put this formulation into a particular kind of a problem. So we will start by putting it on a case that we already, yeah, the potential of this form. So this is my x, this is my v of x, and the v of x potential I am taking without, okay, it's a continuous thing, there is no dip. Okay, so this is the energy that I have for the particle, and these are the turning points x1 and x2. I'm naming them x1 and x2 here. And I have three regions: psi1, psi2, psi3. Three regions. So this is classically forbidden region because the energy of this region, or the potential of that region, is going to be more than that of the energy. That means the kinetic energy is negative. Classically forbidden. Classically forbidden. Classically allowed region. Okay, I have to write the wave function corresponding to each of these region. No? So the psi1 wave function will be of the form. Okay, psi1 and psi3 will be coming of uh, the same exponentially decaying form, a by root p of x, uh, exponential, or what you have here is the limit 1 by h cross x to x naught, not x naught. Here we, our first boundary is x1, x1. So put the limit correctly. So when you're writing psi1, you have to write, you take an x value somewhere here, and from that x you're going to x1. That is a way we are putting the limit x to x1, p of x prime dx prime. That's a dummy variable, and yeah, that's it. Another component will not be there because when you're normalizing it, that component will not be existing. You need to have a normalization which is acceptable at this region. That is the property of wave function. So due to the normalization reasons, we cannot have the another component. This is the only component which is possible. Same way, psi3, I will be having a different constant. I'm taking what constant? I'll take B and C. I'll reserve for psi2, the constant which is coming along with psi2. Okay, then I will take D. D root p of x exponential. Okay, this is actually a decreasing exponential 1 by h cross where to where x2 to x2 to x p of x prime dx prime. Okay, one thing that I want to uh, tell you from here is that if you compare it with the wave function that you obtain for the rigid uh, wall, rigid potential well of a finite length, you'll be having a wave function corresponding to the region 1 and 3. So you may feel that the expression in that case is different, at least with the region psi 1, because there you will be having an increasing exponential at this region. That is because of this integration factor over here. So once you put the limit correctly, you actually have an increasing exponential here on x, but not on this quantity. So that is the difference. This is a decreasing exponential on this particular integration. So if you want, you just put the limit and just integrate it, which way that is normalizable, you can check it. Okay, so this is a way both of these wave functions are consistent because of this integration limits. Okay, so uh, now I have here, you see psi1 is a decreasing exponential on this quantity. Here psi3 is a decreasing exponential of this quantity. So to connect with this wave function, I must use the sinusoidal component in the psi2 region. So my psi2 will be okay, I have only b here, root p of x, and sine. So I can write psi2 as a connection to the boundary x1, also as a connection from the boundary x2. There are two expressions for psi2. So first I'll write it in terms of this quantity. I want to connect from x1 to an point somewhere in the middle. So x1 to x. So this is 1 by h cross integral x1 to x p of x prime dx prime. I have a pi by 4 factor. So that is when, yeah, it's better to write x, where is your x location at a particular case. In this case, x is greater than x1, but of course it's less than x2. Okay, that means your x is at this region. Now Another way of writing SI2 is, okay, I have B C root P of X sine 1 by H cross. I have to start from some X to this boundary. So the location of X is again between the classically allowed region. So x2 P of X prime dx prime plus pi by 4. Again, this is the same limit within which it is defined. It is different for psi 1 and psi 3. That's if you are writing here, your x is actually greater than x2. Here x is less than x1. This is a location where your x is running. This is a location where x is running when psi 3 is being put. Okay, so that is the way we write the wave functions. And now what we can do, see, we have two expressions for psi 2 here. Let us just compare them. Ultimately they are representing the wave function at the classically allowed region, and that means both of them are equivalent, so you can equate them. So if you equate these two expressions, what you will be getting, the expression is of the form like, see, some sign of some quantity is there, but the integration limit is different. So it's like sine of a theta. So it's just like some uh, p sine theta 1 equal to q sine theta 2. So if you have any expression like this, theta's, the angle is connected by using an expression theta 1 plus theta 2 equal to n plus 1 pi. And the amplitude will be connected. Let's write p is connected with q like -1 whole raised to n q. This is a way they connected. Okay, so you can just verify it, the formulas. So if that is the case, you can compare the angles here. Angles are like 1 by h cross x1 to x. That will be just like 1 by h cross x1 to x p of x prime dx prime plus 1 pi by 4 plus 1 by h cross integral x to x2 p of x prime dx prime plus pi by 4 equal to 0. Yeah, not 0, n plus 1 pi. Okay, so here pi by 4 is there, pi by 4 is there, that will become pi by 2, and you can subtract that pi by 2 from the RHS. And what else is there? One h cross is there, which is also common, so that h cross also can go to the RHS. Another thing is the integral is running from x1 to x, a quantity, plus x2 of the same quantity. That means it's a continuation of this integral, right? I can jointly write that as some integral running from x1 to x2 p of x prime dx prime. That is a summation. This will be equal to, if you put the h cross and plus 1 is already there, from that you have 1 pi by 2 is being subtracted, so that will become n minus 1 by 2, right, n plus 1, sorry, n plus 1 by 2 h cross is there, and pi. Yeah, so that is the expression. Now the expression turns to this particular form. So what is this quantity? X1 to x2 p of x prime dx prime. So x1 and x2 are the classical turning points. So this is like it's a if you take something from x1 to x2 and run uh, once again to x2 to x1, that is complete. It's a complete cycle. So when you're running from x1 to x2, that is just a half the cycle of the entire motion. So it's just like half of the closed p x prime dx prime. This is half of it, right? x1 to x2. If you have to complete it, you have to run it from x2 to x1 also. So this is half of closed integral p x prime dx prime, that is equal to n plus half. H cross is h by 2 pi, so the pi is cancelled there. This will become h by 2, and that 2 and this 2 will be cancelling. It will give you something like closed integral p of x prime dx prime is equal to n plus half h cross, sorry, h. So some result that is familiar for you is called Bohr-Summer Bohr-Sommerfeld condensation rule. Something that we have seen in the case of hydrogen atom. We haven't seen something that you may be familiar already. Okay, so what it means actually. So this is actually a closed integral of momentum over a variable position. Momentum over a position. It's happening in the phase space. So the integration is happening in phase space, and you're getting that whatever area that you're producing in the phase space is actually an integral multiple of quantity n, and that n is running from 0, 1, 2, 3, etc. Okay, so what en0 corresponds to? That corresponds to the lower energy level that is possible. So this momentum itself is having an energy dependence. So you can write, oh, you can write it explicitly. It is having energy dependence. As you know, whatever we have written here is root 2 me minus v, that depends upon energy level. So this n equal to 0 corresponds to ground state. Okay, I just want to find out the difference between two nearby energy levels, any two energy levels. I'm taking the nth state now, not the ground state itself. I take an nth state. Okay, that for that I'll get the integration like p of en nth state x prime. Now need to write the expression dx prime equal to n plus half h. What about the next energy level? That is p of en plus 1 x prime dx prime is going to be n plus 1 plus half n plus 3 by 2 h. Or the difference between the neighboring two energy levels is going to be h. So closed integral p dx prime between two neighboring energy levels or the area that covers by two neighboring energy levels in phase space corresponds to h, that is a Planck's constant. So that is some important result that we have from here. Now our aim is to just complete the description of wave function. Okay, so let us continue on that. uh, okay, so this is something that we obtain now. Now what about this psi2 wave function here? Their amplitude is connected by using another expression, so I can just write uh, b in terms of c or c in terms of b, whatever way you want. So we will write it in terms of c. Okay, so c is nothing but, or b is nothing but minus 1 whole to the power n c. Okay, so my psi2 wave function here, this becomes this expression become, okay, I'll write it separately. Psi2 is having two forms now. Psi2 is having two forms. The one is minus 1 to the power n c divided by root p of x sine, in this case it is at the boundary 1, so sine of 1 by h cross integral running from x1 to x p of x prime dx prime plus pi by 4 when x yeah, x1 x x2. Okay, x is between x1 and x, like that. And here this is nothing but c root p of x sine, where our integration is running from some x2 p of x prime dx prime plus pi by 4. Okay, so here my x is again at the same region, so that is a psi2, and that we have obtained already. Now we have the wave function at the second region. Let us connect it with the expression at third region. So the third region wave function psi3 is obtained with some d by root p of x exponential, decreasing exponential, where your minus here you have minus 1 by h cross integral p of x prime dx prime, and the integration is running from x2 to x. Okay, so here your x is greater than x2. Well, what about this d? So this d and this equation, we have to use the connection formula here. What is their relationship? That sine and exponentially decaying quantity is connected, but their amplitude is just for the sine, this is half of whatever quantity is there, right? Okay, so let me just go to that expression here. So this is expression exponential, whatever quantity is there for the exponential, that is going to be half of whatever coefficient we have for sine. Okay, since I have written it in c, uh, this is going to be c by 2. So D is nothing but C by 2 here. So psi 3 is nothing but C by root P of x exponential minus 1 by h cross, okay, x2 to x P of x prime dx prime for x greater than x2. So this is the psi 3 part of the wave function. What about psi 1? In the case of psi 1, exponential form, yeah, there is no change. What about the coefficient here? That again connect with this sign expression. It connect with this sign expression, not this one. So again we know the coefficient is this, whatever coefficient is there here, divided by 2, right? So you take minus 1 whole raised to n c divided by 2. That is going to be your psi 1. So minus 1 whole raised to n c divided by 2. I didn't write 2 here. 2 root p of x exponential minus 1 by h cross integral, uh, here this is like x2 x1 p of x prime ds prime for x less than x1. Okay, so uh, exponential term is half of the amplitude of the sine component. So all these things are now connected. We only have one unknown coefficient, which is c, that we have to find out by using normalization. Okay, psi 1 you obtain, psi 3 you obtain, and psi 2 you obtain. This may be written in the book in terms of, maybe you can write it in terms of d, or you can write it in terms of a whatever. So depending upon that, there will be some slight changes. Whichever way you are using, you can just be consistent on that. Okay, so to put the things on the bracket box, this is our final two things. Psi 1 and psi 3, and we have our psi 2 here. Okay.